Welcome viewers to the fifth segment of the fifth lecture for the online series of lectures for the course of Algebraic Topology 2. In the previous segment, we proved the existence of Mayer-Vitreous sequence for the case of absolute homology groups. We now prove the existence of Mayer-Vitreous sequence in the context of reduced homology groups. For that, we deal with augmented chain complexes. So, the chain map phi we consider this chain map between this augmented chain complex and this augmented chain complex. Okay. So this is a chain map between the augmented chain complexes. This is a claim, we are going to prove it, okay? Chain complexes, and also psi from this chain complex to the chain complex C of K, comma, epsilon is another chain map, is a chain map between the respective augmented chain complexes. Okay, so how do we see it? This is because both phi and psi are augmentation preserving maps, okay, which can be seen from the following commutative diagram. Okay, so let me draw this commutative diagram. So on the top there is an exact sequence 0 to C0 of A, from C0 of A to C0 of K0, direct sum C0 of K1, and then from the direct sum of these two pieces to C0 of K, and then from C0 of K to 0, the trivial group containing the identity element only. And there is the sequence 0 to Z, and then from Z to Z plus Z, Z direct sum Z, and then from Z direct sum Z to Z, and then from Z to 0. Okay, so this is the augmentation map epsilon A, and this is the augmentation map epsilon 0 direct sum epsilon 1, and this is the augmentation map epsilon. Okay, so here epsilon A, epsilon 0, epsilon 1, and epsilon denote augmentation maps for the chain complex C of A the chain complex C of K0, the chain complex C of K1, and the chain complex C of K, respectively. Okay, good. And one defines these. So I call this map phi minus 1 and this one psi minus 1. This is phi 0 and this is psi 0. Okay, so phi minus 1, so this z is in dimension minus 1, this z plus z is also in dimension minus 1, this z is in dimension minus 1, and these are group homomorphisms in dimension minus 1. Okay, so how do we define these maps? Phi minus 1 is a map from the group Z to the group Z plus Z by phi minus 1 of n is equal to n comma minus n, and psi minus 1 is the map from Z plus Z to Z by psi minus 1 of m comma n is, so psi minus 1 acts on a pair and spits out an integer, and that integer is going to be m plus n. Good. So now, given these definitions, we want to prove that this is a commutative square, and also we want to prove that this is a commutative square. Okay, so let's do that. So in other words, we need to prove, so let's try to prove that this is a commutative square. In other words, we want to prove that the direct sum of epsilon 0 plus epsilon 1 composed with phi 0 is equal to phi minus 1 composed with epsilon a. This is what we need to prove first. Okay. So now the first thing to note is that this map I hash, okay, and the map J hash, they can be easily seen to be augmentation preserving. Okay, so what does it mean by augmentation preserving maps? It means that the following two diagrams are commutative. What are those diagrams? C0 of A is mapped to C0 of K0 via this map I hash, via this group homomorphism. which takes zero chains on A to the zero chains on K0, and there is this augmentation map epsilon A that takes C0 of A to the additive group of integers, and there is this augmentation map epsilon 0 that takes C0 of K0 to this additive group of integers, and this is the identity map. Okay, so this is a commutative diagram. It can be easily seen to be a commutative diagram by using the definition of augmentation map, which means that epsilon 0 composed with the map, the homomorphism I hash at 0 is equal to simply epsilon A. And another thing is that J hash is also augmentation preserving, meaning that the following diagram commutes C0 of A to C0 of K1, and then from C0 this is J hash at 0. Okay, and this is Z, this is again Z, this is epsilon A, this is epsilon 1, and this is the identity map. This is commutative again, which means that it can be shown that epsilon 1 composed with J hash at 0 is equal to epsilon A. Okay, this is equation number 20. Okay, so equation 20 can be proved very easily using the definition of augmentation maps. Okay, now given a zero chain C0 and C0 of A, one has epsilon 0 direct sum epsilon 1 composed with phi of 0 and this composed map is acting on C0, and what does it give us? So I leave the direct sum of these two augmentation maps as they are, and then apply the definition of phi p, taking p to be equal to 0, and that gives us I hash at 0, C0, comma minus J hash at 0, C0. Okay, and this is using equation 10, which is the definition of phi p. And then, epsilon 0 hits the first component only, and epsilon 1 hits the second component only. So this gives us epsilon 0 composed with I hash at 0, and this composed map acts on C0. Similarly, there is a minus sign in front, and then epsilon 1 composed with J hash at 0, and this composed map acts on C0, right? Now, we know that from this equality, from equation 20, we see that this is nothing but epsilon A C0, and this is my minus epsilon A C0. So follows from equation 20 using 20. So what is this? This is from the definition of phi minus 1. We have defined it earlier, right? Remember, phi minus 1 acting on n, where n is an integer, splits n comma minus n, splits this pair belonging here. Okay, so according to this definition, is going to be phi inverse acting on epsilon a c0. Okay, and this is nothing but phi minus 1 composed with epsilon a acting on c0. Right, this is equation number 21. So from 21, one concludes that epsilon 0 direct sum epsilon 1 composed with phi 0 is equal to phi minus 1 composed with epsilon a, right? So this is epsilon 0 direct sum epsilon 1 composed with phi 0, this path which takes c0 of a to the direct sum of z with itself. Okay, and phi minus 1 composed with epsilon a is this path via which c0 of a is going to the direct sum of z with itself. Okay, in other words, this square commutes. Okay, good. Now about the second, about this second square, commutativity of this second square. So we need to prove that epsilon composed with psi 0 is equal to psi minus 1 composed with epsilon 0 direct sum epsilon 1. This is what one needs to prove. Indeed, for C0 belonging to the group of zero chains on K0, and C1 belonging to the group of zero chains on K1, one has epsilon composed with psi 0 acting on this pair, on a pair belonging to this group, C0 comma C1, is equal to epsilon. Now I use the definition of psi p that gives k hash at 0 acting on C0 plus L hash at 0 acting on C1. This is what we get by using the definition of psi p. Okay, so this is equation number 22. Now k hash and L hash are easily seen to be augmentation preserving, to be augmentation preserving. What does that mean? In other words, the following diagram commutes. One can check that the diagrams below are commutative. C0 of K0 is taken to C0 of K via this map K hash at 0, and there are these augmentation maps epsilon 0 and epsilon. This is Z, this is Z, and this is the identity map ID. Okay, so in other words, one can check that epsilon composed with K hash at 0 is equal to epsilon 0. This is one commutative diagram from which follows this equality. There is another commutative diagram which is from C0 of K1 to C0 of K, which is L hash at 0. And there are these augmentation maps, in this case, epsilon 0 and epsilon. Sorry, this is epsilon 1. This is epsilon 1 and that is epsilon. This is Z, this is Z, this is the identity map. This is a commutative diagram, meaning that one has epsilon composed with L hash at 0 is equal to epsilon 1. Okay. So from the equality from these two equalities, one obtained from equation number 20 from 22 one has epsilon composed with psi 0 acting on C0 comma C1 is equal to what? The first one is epsilon composed with K hash at 0. This is epsilon 0, C0 plus, and then epsilon composed with L hash at 0. This is epsilon 1, this is epsilon 1 C1. So from the definition of psi minus 1, which is psi minus 1 acts on a pair m comma n and spits out an integer which is m plus n. This is how psi minus 1 is defined. So this is psi minus 1 acting on the pair epsilon 0 c0 comma epsilon 1 c1. Okay, and this is nothing but psi minus 1 composed with this direct sum of the augmentation maps epsilon 0 direct sum epsilon 1. Okay, and the whole thing acts on the pair c0 comma c1. Okay, so let me erase things on the right. So we have epsilon composed with psi 0 is equal to psi minus 1 composed with the direct sum of epsilon 0 and epsilon 1. So which means that the square on the right also commutes, because we go from C0 of K0 direct sum C0 of K1 to Z via this path, which is epsilon composed with psi 0, and then it's the same as taking this path, which is psi minus 1 composed with epsilon 0 direct sum epsilon 1. Okay, all right. All right, so I think it's a good time to take a break. I'll be back with the rest of the proof of the Mayer-Vitteris sequence in the setting of reduced homology groups. Thank you for attending this segment.